We are very happy to have Guillermo tell us about the geometry of constant function market making.
Cool. Well, thank you for having me. This paper is a bit weird. Constant function market makers, I guess, now there's probably not that much of an intro needed, but this paper essentially kind of takes a totally different perspective on constant function market makers, which is purely a geometric one. Which is probably a bit alien to most of us considering kind of these algebraic representations and things like that. So this is joint work with the usual suspects, Tarun, Theo, Alex, and Shitij. Cool. So very quickly, why yet another talk on constant function market makers? Isn't there literally anything more interesting to talk about in 2023? So in some way, this is yet again an interesting talk because it's not a paper in itself. One might think of it more as kind of a short monograph, which attempts to take a bunch of results that are known in the field and put them under one consistent and simple framework. So to do that, we have to trace a little bit of the history. So first things first, in late 2018, which seems essentially ancient now, Uniswap appears. And there were two sources for Uniswap. The first is 250 lines of Viper code and GitHub. And number two was this weird paper called A Formal Specification of Constant Product Market Makers, I think by Zhang et al. And essentially, at the time, they were interested in things that happen on smart contracts, which were things like round-off errors. So, of course, we talk about the real numbers as if they're like a real thing, but when we actually get down and code it on a computer, you have finite fixed precision. And so there was the natural questions that emerge are, can you do things like accidentally, when you take out liquidity, make more money than you actually put in? Immediately after that, another paper appears, just analysis of Uniswap markets, and then asks the economic side of the question, which is, this thing seems to work in practice, but why the hell does it work? It seemed to track the market prices as people would expect. It seemed to be pretty difficult to manipulate, and people weren't doing that too much at the time until essentially MEV was formalized. And it showed that not only was Uniswap an interesting market to think about, but there was also this other thing called Balancer. And Balancer seemed to have very similar properties. It was a generalization of Uniswap, that much was clear. But there was a natural question of what other things fit into this framework, right? So certainly constant products and constant geometric mean market makers. And at the time, there was this other thing called curve. And they all seemed roughly similar, but automated market making seemed like too large of an umbrella to say anything interesting. So there was a question of what was a natural generalization of these two, and at the time, then three market makers for which we could say interesting things about. And so at the time, what was important was this notion of using these pools as oracles. And so this other weird paper comes out, which actually coins the term constant function market makers, which you've probably heard at least 500 times today so far. And this is in 2020. And one might think at the time this was niche esoterica, and we expected it to stay niche esoterica for a long time. But then in 2021, there's about 50 papers mentioning CFMMs, and in 2022, there's about 80 that come out since. And I think I just checked yesterday, and there's like 110 as of this year or something like that. So, again, so the question still is why? We have 200 and some odd papers on CFMMs. Why yet another one? And so, of course, first things that happens in the field is after 3 years, you actually do get a bunch of crazy, interesting, and fascinating results. And there's many new ones that were not intuitive at the time, certainly, and honestly, sometimes still aren't. But many of these ideas are derived from this algebraic point of view, from the view of there exists a trading function. This trading function has certain properties, and then we go and then derive something out of them. So fundamentally, though, CFMMs are kind of geometric objects. We'll see what I mean by that in a second. But the point is that the geometric objects have very intuitive properties, both in the sense of there exists some algebra over these geometric objects that is reasonable, but also kind of, you can picture them. When you first thing that happens anytime someone presents Uniswap is, of course, they present the hyperbola that Uniswap has for its reserves. So can we show, based on this idea, a lot of the results that we now know for CFMMs and generalize them ideally? So maybe we don't require things like differentiability. Maybe we don't require things like homogeneity. Okay, so what do we mean by an algebraic framework? Right, Uniswap has possibly, there's a one homogeneous concave non-decreasing representation, which is square root of R1 times R2, where these are the reserves. I'm not introducing any of this stuff because I assume approximately 99.9% of the audience knows this stuff. So one representation is this. Of course, you could square both sides because both sides are non-negative, and certainly that's also equivalent to the second line. But you can take the log of both sides as well. Perfectly reasonable. Indeed, any non-decreasing function would work. Actually, well, strictly increasing at exactly one point, which is k. But and the point is that the trading function is simply one parameterization of kind of an underlying object. And there might be some that are more useful to work with than others, but that's okay. Fundamentally, it's all kind of the same thing. Okay, so functions. Let's take this to an extreme. Let's just totally drop the trading function as an idea. Just we're going to define everything in terms of a set, and then we're going to recover all of this, properties that we know and love from constant function market makers based on just a geometric definition. And so the question is, just how far can we take that? Cool. So let's start. First, I'm going to do a weird thing. So we're going to define a constant function market maker, and we're going to write it as a set S. So I will conflate two things. I'll conflate the set S and the constant function market maker itself. And we're going to call the set S a reachable reserve set. So the set S is going to be a subset of all non-negative n vectors, and it's going to satisfy exactly two properties. The first is that it's non-empty. That's kind of easy. It's non-trivial. Number two, it's closed. And the question of like what closed and open actually means in practice is kind of silly. So I'll just call it a technical condition, as we usually do in these areas. And then we're going to say it's convex, and that has the interpretation that tendering, for example, more of an asset to the CFMM will not increase its price. And then number two, which is actually, funnily enough, also a technical condition, but we'll reference you to the paper, is that it is upward closed. So R is going to be some reserves, and we're going to say that R is in the set S. So this is the constant function market maker. And if some set of reserves is in S, then any set of reserves that is at least as large element-wise as that set of reserves should also lie in the set. And that's it. Those are the only two assumptions. How far can we go with just these two things? Okay, so of course, this includes the standard definition that we all know and love. Certainly, we can define the set S as a set of reserves R such that some trading function, whatever it is, whatever your favorite one is at least as large as K, which is your constant. So the classic case is, of course, as we all know, Uniswap V2, and that's simply define the set S to be the set of reserves R such that their product is at least 1. Okay, so here's one immediate consequence, which is already not obvious. These reachable sets, those two conditions, are closed under the following 4 operations. So they're closed under Minkowski addition, right? So this is, you take any point in the two sets, you add those 2 points, and you add that to the Minkowski added set, right? And of course, you can see that this is closed. This is the closedness is actually not obvious, but certainly not empty. And it's certainly kind of non-decreasing in the sense that I was specifying previously, right? Any trade that is, any reserves that lie in the set, certainly any reserves that are at least as large element-wise will also lie in this new set. It's also convex. This is also not super obvious, but it's standard. Number 2 is scaling. Scaling by a positive constant clearly preserves all of the properties that we want. Intersection certainly does. And then non-negative matrix multiplication. That one's a little bit more annoying, and so I'll leave it as an exercise to the reader, but you're welcome to do so. And so one example of set addition is, of course, concentrated liquidity in Uniswap V3. So these are concentrated liquidity ticks. One of the S1 is one concentrated liquidity tick. S2 is a second. And then, of course, you can consider S1 plus S2 as being the same as being allowed to trade in each tick. So one may consider, for example, Uniswap V3 as the addition of all of its ticks, and it is, of course, itself a constant function market maker in the sense that it satisfies the definitions. Okay, so now the natural question is, great, we have this set S. Can we recover the, what we call the trading function, right? We've defined this thing. We want to say it's equivalent to constant function market makers. We certainly have that it includes the normal definition. Now, can we recover the normal definition from this? And the answer is yes. And we're going to define it as the following thing, which is we're going to take, so phi of R, which is going to be our trading function, we're going to define it as the following. We're going to scale R by some constant lambda, and then check whether it lies in a set. And why does that make sense? Well, essentially, if lambda is greater than 1, and you can see this from this picture, for example, then certainly we're in the set because we have to be scaled downwards, right, to lie on the boundary. And then, on the other hand, if we're less than 1, we're kind of on the left. Ooh, does this have a pointer? Actually, I don't think it has a pen. If we're on the left-hand side of the set, right, then we have to scale upwards. So lambda must be less than 1. And so therefore, you are not in the set. And so actually, funnily enough, this is called the canonical trading function. We call it the canonical trading function because it's the unique, one homogeneous, concave, and non-decreasing function corresponding to any CFMM. So any two representations of a CFMM that satisfy those properties are actually the same up to a constant. Great, we've recovered that case. Now we're going to define something a little bit weirder, which is called the liquidity cone. And this is going to be the most important object in this talk. So we're going to define it as, if you recall, the canonical trading function had this little r over lambda. It's the same thing. All we're going to say is this is a set of reserves such that when scaled by a positive constant, lie in the set, right? And the set is simply the reserves and the constant put together. Okay, so there's a cone because of the fact that if you take any element in K, you multiply it by any constant, any positive constant, that is also an element in K. And so we can see the picture for Uniswap V2, which is take any point here, scale it, if you draw the line from 0 to any point, and you scale it by any amount, it certainly still lies in the set itself. And you can see here is the ISO curve carved out by the canonical trading function. Okay, so I'm just rehashing the definition of the liquidity cone. Then why do we call that kind of the canonical object? Well, first, it easily contains the reserves, the reachable set, right? Because the reachable set is, of course, a set of reserves R such that R comma 1 is in K. And you can see that because you can just plug in 1 for lambda up there, and you see that that's true if and only if it's an S. And then number 2, of course, it gives the canonical trading function, right? By definition, that was the trading function, in other words, the lambda, largest lambda, such that R over lambda is an S. And of course, that's exactly the definition here, if plugged back up there. Okay, so where are we so far? I'm going to start drawing this little treasure map, as someone reviewing the slides lovingly called it. So we have reachable set S. We can, of course, we have a bijection between reachable sets and liquidity cones, and we also have a bijection between liquidity cones and trading functions. What are we going to go from here? We're going to start adding things to this, and then we're going to have a bunch of operations that we can trace to get from any one place to the other. Okay. So we're going to talk about the dual cone. So the dual cone is this classic object. If you ever have a convex cone and you've ever studied convex geometry, the first thing that should come into mind is like, what is this thing's dual? It tells you some other alternative perspective on exactly the same object, and it often has very beautiful economic interpretations. So a closed convex cone has a convex dual cone, which we're going to call K star. The definition is not super important, but I'll go over it just for fun, which is the dual cone is defined as a set of vectors which have non-negative inner product with every element in the cone K. So we're going to call that K star. Don't worry too much about the definition. It's not that important. But the point is, it's another representation of the original cone. And what do we mean by that? We mean that if you take the dual of the dual, you actually recover the original cone. So there, again, there's another bijective operation between a cone and its dual. Okay, so now we have another, enter has arrived, right? And we have, liquidity cone to the dual cone, and there's a natural question of, okay, what's next? So what is the dual of a liquidity cone? Here's a definition. That term, if you're familiar with the notion of a portfolio value function, should look very suspicious, right? You have something like, oh, for all R in the reachable set, in other words, all reasonable reserves for a constant function market maker, the inner product between a cost vector and R should be at least as large as some value. So for those who are familiar, this actually looks a lot like the portfolio value function. And the reason why is, of course, this is the smallest of all C transpose R. But of course, it's the same thing as saying that's the largest of all eta, so to speak, which are that are smaller than all C transpose R. So that's, again, not super important, but the point is you can write the portfolio value function as simply being kind of the equivalent of the trading function, but for the dual cone. Okay, so now we have a last domino, which is cool. We have a reachable set. We can go to the liquidity cone, trading function, dual cone, and portfolio value function. Now, after eating our vegetables for approximately 10 minutes, we can do some real things. So we can start from any object and follow the arrows to get any other object, right? We have bijections between any of them. So in some sense, they're all equivalent. Now, what can we do with that? So let's do a classic case. So this is a result from 2021, which is, of course, every trading function has a portfolio value function. That's well known. But actually, what was not well known is that every portfolio value function corresponds to a unique trading function. In this case, a unique canonical trading function. And so what does that actually look like? So with that, we actually get a standard weird result. So this is already a bit more symmetric than is known, which is the portfolio value function is the smallest over all strictly positive reserves of C transpose R divided by the canonical trading function of R. On the other hand, right, so this is a known result, so to speak, and it's not obvious. You need to actually go through and plug in all the stuff, but it's mechanical, right? You have all of the bijections and you can simply plug them in and get a result. What's not obvious is the following, which is actually the trading function looks the same, right? Just replacing phi for v and c for r. So this gives a very nice, lovely equivalence between the portfolio value function and the canonical trading function that, at least to our knowledge, is not known. And it's kind of nice, right? It highlights that in some sense, they really are duals of each other in a very concrete, weird way. And so this is a more symmetric form than was known at the time. Okay, so another thing that we had is, if you remember back at the beginning of the presentation, I mentioned that there's these operations on the sets, right? So I said a reachable set is kind of, these things are closed under certain operations: addition, intersection, non-negative scaling. Okay, so the next natural question is, okay, let's trace another path. Start from the reachable set, go to the liquidity cone, go to the dual cone, and then go to the portfolio value function V. And the next question is, what do those operations, which mind you are over sets, correspond to over functions? Right? This is weird, right? These are objects from essentially like different types. So we're about to do something kind of odd, and it's going to look, of course, obvious in retrospect. But I'm telling you, this is not totally clear. Okay, so how are we going to do this? We'll start with a reachable set. So of course, we can start from any portfolio value function and then go back to its reachable set. We're going to call our reachable set S sub V for a given portfolio value function V. Okay, and here's the deal. S of the sum of portfolio value functions is, of course, equal to the sum of the reachable sets. Another thing is that the scaling of a portfolio value function and the set corresponding to that is actually equal to the scaling of the set. And affine, or sorry, in this case, linear precomposition, of course, equals the linear with the transpose composed with the set. This is weird. So parse these symbols extremely carefully. On the left-hand side, right, we're talking about addition and pointwise addition over functions. On the right-hand side, we're talking about the Minkowski sum of two convex sets. Similarly, the scaling here is pointwise scaling for a given function. Yet on the right-hand side, we're talking about scaling for a given set. This is not obvious, right? And so the types here must be parsed extremely carefully. And of course, there's some fancy bullshit mathematical way of saying it, which is that there is an operation preserving isomorphism between the sets S and the functions V. Okay, so let's take one more peek. Again, it's kind of crazy, right? We've given this thing, which is all these objects are all equivalent. We can go from any one of them to any other one of them. And so we can work with whatever feels easiest. So for example, I will challenge you to find what the corresponding operations are for the reachable set given the trading function. And I will tell you that it's really not obvious. But for the portfolio value function, it looks hilariously simple. And that's kind of the power of this idea of fundamentally we have this geometric object. We have many ways of specifying the same geometric object. What can we do with that? And how do we go from one place to the other? Okay. So quickly, the paper has many more results. Actually, this is I would say it's less of a paper and more of a tome. So I apologize for any readers. Would highly recommend you skip through to find the things that you find interesting. But for example, there's things like there's equivalences for path independence that don't require the notion of histories. So this is a common thing that happens is you start with a notion of history, you try to show that something is path independent. Here's a geometric description of what that means. That's relatively simple. We also extend a lot of the results to the single trade case, actually, where you are allowed to have fees of any kind of variety. We show that the equivalence of the routing over constant function market makers and actually the Minkowski set sum, so here as given, we call it CFMM aggregation, are the same. Actually, they're identical. Not just they're identical in a concrete sense, they're identical in the same program that you get from one, you get to the other. We have connection to prediction markets via a kind of geometric point of view here. And this is actually work from Gillo, Lapide-Vigatti, and Wagner, which is lovely work. And so we do a short paragraph showing some of the same derivations in a geometric point of view. And then there's many, many more results that might be interesting or might not be, but I encourage you to look through it. And so for that, thank you guys. And here is the QR code of the archive link. So I guess I don't know if there's any questions.
Is it fair to say that your paper provides the theoretical foundation for those replicated market maker concepts?
So replicated market makers actually has a a funny version of this, which nowadays looks hilariously unnatural, but at the time was like cool. So this is like the kind of, there's a pretty way of putting it, a pretty mathematical way of putting it. I think this is the right one. Maybe not. Maybe you can find a nicer one, but.
Yep. Maybe building on that question, it's great that we have all these representations, and I think you did a really nice job connecting them. But one representation you don't explicitly call out is, I guess, what we call the demand curve, which is basically how much of the risky asset do you hold at different price levels, right?
Ooh, yeah.
And I know that you've thought about this representation and have written a paper, a very early paper about it. And in some sense, it's also quite intuitive because it's kind of what comes out of like Meyerson type formulations.
Mm-hmm.
Like that was essentially the object Philip was talking about as well. So how does that object fit into your framework, and why do you not include it, I guess?
So it's very similar, I guess, to. So, if you're a physicist and have you ever like looked at the supersymmetry diagrams, right? There's always like this hole missing. And so this is like how physicists conjecture that there should be like a particle there. So there should be a particle there, right? And there's something weird about this diagram in that it's not symmetric. So exercise for the reader is, what is that thing that's missing? What does the reachable set S, what is the equivalent for the dual? Take a look at that. And I think it's similar to what you're talking about. Okay.
Other questions?
Please don't ask too many hard ones.
Maybe I can ask a question. So the portfolio value seems like, in a mathematical sense, like a support function on the convex set. So
Yes.
if you were to express these results in terms of support functions of the convex sets,
Yes.
what would be the equivalent, or is it really just using the analogy of support functions?
So it's exactly you're totally right. This is exactly the support function. Oh, this is for.
Oh, sorry, I keep it.
Yeah, this is exactly a support function for the reachable set S. So what's the portfolio value function and for the reachable set S, and then you get kind of the standard properties from the properties of the set itself. On the other hand, there's kind of not a nice duality for those reachable sets as far as we know, it's much more nicely expressed via the liquidity cone. But it is exactly what it is. I mean, the portfolio value function V corresponds exactly to the support function for the set S. And the trading function V corresponds exactly to the missing, supermassive weakly interactive particle up on the top right that we cannot see.
There's a small literature on thinking about mechanism design and the support function characterization.
Oh, yeah.
By Alexei Kushner. This might be interesting to look at because they provide characterizations of incentive compatibility in terms of support function.
Interesting. Okay, I should take a peek at that. Yeah, actually, can you send me the reference afterwards? Yeah, we've been having fun with Tim's 21 lectures in algorithmic game theory and rewriting it in convex terms. So that'll be an interesting set of notes. Cool. I think we're 10 minutes under, so maybe I speed ran the presentation.
Thank you. Let's speak again.